for volume, I would give you the other two variables. Or I would ask for the mass, and the other two variables are given to you. So you should be able to rearrange this equation and solve for any of the three variables, not just always density. Does that make sense?
Yeah.
Whenever you see any of the equations that we're going to talk about in this class, you have to get used to doing that. Even in 101, it's the same thing. You have to get used to solving the actual problem in all the different ways possible. Okay, let's go back to metric prefixes right here. Now the most common, I would say, three conversions that you see the most is 1 kilogram or 1 kilometer, 1 kilometer, doesn't matter what base unit I have, but it's 1 kilogram equals how many grams? 1,000. You also hear about this one. 1 liter equals how many milliliters? 1,000 milliliters. What about centimeter to meter?
100.
Yeah, 100 centimeter equals 1 meter. Those are the three most common kind of metric conversions that you're going to see. Again, I'm just using this as an example, right? It could be centiliters instead, or centigrams instead. I'm just using meters, liters, and grams, just changing up the units, that's all. Now, let's say you're dealing with something that's really large or really small. When you're looking at that, it becomes easier to kind of have the same consistency, how you read this table. So the way you can read this table, there's two different ways. The easiest way is always in front of the prefix, you put a 1. So it doesn't matter what I'm talking about, wherever you see a prefix, you're going to put a 1. So I can say 1 gigagram, right? And then, looking at the base unit, because I'm talking about grams, I'm going to look at giga and notice it's 10 to the 9th. That's the multiplier. So I can write it like this. And this makes sense because giga is very large. So you expect a very large number here when I'm talking about the multiplier. So I always put a 1 in front of the prefix. Even if I'm talking about something small, you do it the same way. If I'm saying 1 micrograms, right? Micro is very small, so it's going to take up a very small part of a gram. If you look at micro, the multiplier is 10 to the negative 6. So you would write it like this. So it's keeping it the same. You always put a 1 in front of the prefix. You notice that was done for this one here. 1 in front of the prefix, and then kilo is 10 to the 3rd, which is 1,000. So you got that. Now, if you look at the other two, notice the 1 isn't in front of the prefix. Now the 1 is in front of the base unit. So they change it up. And this happens a lot when you're dealing with really small units. So anything below basically centi, or deci actually, anything below that. The way that's written is, notice here I wrote it like this, but I can also write it like this. so here it was to the -6. Now it's in front of the prefix, but it's +6. So 1 gram is 1,000,000 micrograms. That makes sense because micro is very small. You need a lot of them to make up 1 gram. So both ways work. It's up to you which way you want to do it. It depends on how you were taught in high school, if you took high school chemistry. In the textbook, they'll stick with this method. I was taught this method, so both are interchangeable. They both mean the same thing. You just have to understand you're dealing with something very small. So 1 or a gram of it is going to be a very small component. Or 1,000,000 micrograms is going to make up 1 gram. So we're going to try this on number 6. Number 6, you're going from one prefix to another. Now you can go directly, but I always recommend going to the base unit first. The base unit is meters. So if I go to meters before I go to decimeters, it's going to make my life a little bit easier. You can go directly from micro to deci. You can do that. It's just you need to be able to figure out, okay, what exponent is that really? I'll give you a few minutes to kind of set it up, see if we did the same thing. Micro, what's the multiplier?
-6.
Yeah, 10 to the -6. So here, I'm going to put a 1 in front of the prefix with 1 times 10 to the -6 meters. Okay, then I have to go, I'll do the setup, I'm just writing down the conversions right now. Meters to decimeters, what would that be? What's the multiplier?
-1.
-1. So again, putting a 1 in front of the prefix, it's going to be 1 times 10 to the -1 meters. Okay, now when I do the setup, I have 10 micrometers. Now I'm going to set it up again. Micrometers needs to cancel out. If I look here, I have a 1 in front of the micrometers. So I'm going to put that here. And then 1 times 10 to the -6 meters. Okay, my second conversion was this one here, right? I want to be left with decimeters. That's going to go on the top or the bottom? Top, right? So I'm going to put 1 decimeter on top, 1 times 10 to the -1 meters on the bottom. Now, which one is larger, micro or deci?
Deci.
Deci is larger, right? So if I have 10 here, would you expect the number to be larger or smaller when I'm talking about deci?
Much smaller.
Much smaller, right? Much smaller, because I'm talking about decimeters, which has a larger multiplier. It's -1 versus -6. Now, if I look at this, you technically don't need a calculator, because when you look at exponents, here I'm dividing the exponent, or dividing 1 times 10 to the -6 by to the -1. So what do I do to the exponent part? You subtract. So it's going to be 10 to the what? -5, right? So -5, I would just have to move the decimal place to the left 5 times. So here I have it, or let me write it here. I have 10, I'm going to move it 1, 2, 3, 4, 5.
Why would it be -5?
Oh, because here I have -6, and it's divided by the -1. I just subtract the exponents.
Oh, okay.
Yeah. So I'm just doing -6 minus -1.
Oh, okay.
You get -5. You can use a calculator just because they're the same. I can just do it in my head. So if I look at this, how many zeros do I have? 1, 2, 3, 4, 5. So yes, I do expect a very small number, because again, decimeter is a lot larger than micrometer. So if I have 10 micrometers, if I put that in a unit that's even larger, the number is going to be extremely small. Instead of micro, if I went from micrograms to nanograms, what should happen to the 10? It would get larger, yeah. So if I went, looking at this, if I went from micrometer to nanometer, right? If this was 10, I should expect this number to be even larger. Notice it changes by a factor of 3. So I would move the decimal place 3 more times. And you got -5, right? You look at this. This is -1. This was -6. It changes by a factor of 5, right? So you can do it directly from micrometers directly to decimeters without going to meters. But normally if that happens, a lot of people get confused, because if I do something like this, where I go from a really small unit to a really large unit, it throws people off. And then they start with the exponents, it just becomes a hot mess. They end up canceling it out. They're like, oh, -6, 6. Oh, it should be, right smack in the middle. But it's not. Someone had a question, yes?
You still have to be careful with sig figs.
With this, no. In the sense that if you look at it, the first number will determine it, but you don't have to ever worry about these. They will never limit you. So if you look at this, here, how many significant figures do you have? Just 1. So technically I should write it like this and not put that 0 there. Because if I put that 0 there, then that 0 is significant. So I just have 1 significant figure. This should still have 1 significant figure. So your starting value will dictate it, not these guys here. These metric prefixes, they will never limit you. Thought I saw an N. No? Okay. What if we do now number 11? we're not gonna do, but I will give you the answer. That way you can check if you did it correctly. Number 7, with the correct number of significant figures, you should get 53 liters. So that's the answer to number 7. Make sure you try that on your own. Number 8 is asking you how many complete cakes can you bake. So you're going to get a number that looks like this. Now it's asking you how many complete cakes. So how many would you say?
9.
Yeah, just 9 cakes. That's it. Because you're not going to make 0.65 of a cake, right? It's just asking you how many cakes.
Some people would.
You can make like a mini cake, maybe half of a cake, but not 0.65. So this one you should get 9 cakes. Okay, let's try number 16. This one's considered a hard one. So do I want to do this one or this? Yeah, let's do 16. Read through it, write down the given information, try to figure out what they want. While you're waiting, I'm going to pass out chapter 3 lecture problems. I'm going to pass that out.
This is just one paper.
Are you ever going to turn this in?
volume of a cylinder. So there's a reason why they're giving you that. Now, they give you the diameter, the mass of the cylinder, and they want you to figure out the thickness. What are they talking about when they say thickness?
The height.
Yeah. They're talking about the height. So I'm looking for H. That's what I'm looking for. Now, since they give you the diameter, if I'm looking at this situation, notice I'm given the mass and the density, right? So if I'm given the mass and the density, what can I solve for?
Volume.
The volume. So if I know the volume, I know this, I know what pi is. Do I know R? Yes. Yes. I know the diameter. I can figure out the radius. I have that. Can I solve for H? Yes. You can solve for H. The only thing that you have to keep in mind is notice the units. Diameter is in inches. So I'm going to figure out the radius. It's going to be 1.5 inches. I want to convert this to centimeters. Remember, 1 inch equals 2.54 centimeters. You're 3.81. Exactly, I believe. I think. Yeah, it should be exact. Okay, so if I look at this, I figured out the radius. That's going to be helpful in this situation. So I got R, I know pi, I need to figure out V. So I have mass over volume. If I'm solving for volume, what's the equation? M over V. Yeah. And are these correct units? Am I good to just divide the two? No. Why can't you just divide these two? Well, you're solving for V, right? Grams cancel, you're left with 1 over 1 cubic centimeter, which is cubic centimeter. So it is possible for you to do that. Now, this number, you don't want to cut it off. You don't have to write it all out. I'm just writing it all out. But you could cut it off here, but keep it in your calculator. Don't erase it. Because I'm not done doing the math. This is just an intermediate step. My final answer, I'm not solving for volume, I'm solving for H. So I have the volume, and I'm going to solve for my height. So notice how if you had this in the calculator, you wouldn't need to erase anything, because look at the first step. You're going to end up getting that number. You can put this part in parentheses, pi times 3.81 squared in parentheses, and just divide the two. You can do that in one step. Don't forget to square this. Okay, what units do I end up here? I have cubic centimeters and centimeters squared.
Centimeters.
Yep, just centimeters.
Means you have to multiply by 10.
Yeah. Because all I wanted is in millimeters. You would just move the decimal once. Okay, in this situation, My first equation I used, all I did was division. My second equation I used, all I did was multiplication and division. To go from inches to centimeters, all I did was multiply by 2.54. So anywhere in there, did I say adding or subtracting? No. So all I did was multiplication and division. So what do I keep track of? Significant figures. If I look, all of them have how many? 3. So my final answer should only have 3. Now when I do this, I end up getting 0.0141 centimeters, but they want it in millimeters. Centimeters and millimeters, they only vary by a factor of 10, 10 to the 1, right? So this should be what? Who's smaller? 0.141. Centimeter, right, is larger than millimeter. So your number here should be larger than this number here. All you do is move it one place to the right. So that's going to be the thickness of your silicone cylinders. Because remember, if you have like 5 centimeters, that's 50 millimeters. It's 10 times the amount. Oh, because 1 inch equals 2.54 centimeters. So that's how I did the 3.81. And if you notice, we've used that conversion a lot. It's very common. Yes?
So on the top it's centimeters cubed, and the bottom is centimeters squared. So it became centimeter because you subtracted those two, right? So it's division?
Yes. You can look at it like this too. This is centimeters times centimeters times centimeters. You're dividing by centimeters times centimeters. You're going to be left with one of them, because 2 of them will cancel out. Yes.
And then when you were finding the volume for mass over density, you said that it was okay that you had your centimeters cubed because grams were.
The grams would cancel, and you're solving for volume, right?
So I thought
So-
that was a division.
Yeah, because when you divide this right here, this is grams over grams cubic centimeter. The grams cancel, and you're left with 1 over 1 cubic centimeter, which is just centimeters. Or cubic centimeters. So your units are canceling for just the grams. That makes sense because you're solving for V. Your grams should cancel. You should be left with a unit that's associated with volume and not mass. Now, if you're looking at that and you're like, I don't understand how in the world 1 over 1 cubic centimeter equals centimeters cubed, you need to review your math. This is very basic algebra. Yes?
Couldn't you solve it by just enlarging the cylinder? Like, let's say it was a disc, right? And you enlarge it to make it look like a cylinder, and then draw a triangle within, and then we know the bottom leg would be the radius, so it would be like 1.5, and then use like cosine or whatever
Yeah.
to get the other legs.
You could do that too, but I'm not giving you those equations, so you can still do it, but I would just stick with,
Okay.
since I gave you that equation, stick with that. You can do that as long as you show your work. Yeah,
Which one?
you're good.
61.
Okay, this one's considered a harder problem only because you're doing multiple steps. You're using 2 different equations, right? It's not straightforward. I give you the diameter in inches, not the units that it should be. So you have to kind of work that out before you can go on to the next step. Number 14. This one, you should have no problem doing, because all you're doing is going from one speed to another, just in different units. I tell you the runner runs 4,875 feet in a certain amount of time. You have to calculate the speed in miles per hour. So go from feet to miles and minutes to hours. So you should get 8.09 miles per hour for the run. I'm going to skip for now. Once we cover 3, you'll see this. But you could still do this problem, just because it's words that you may have never heard of, like, or you have, but you're like, what in the world? It's in chemistry, a mole. Or like this J, which represents energy, which is joules. You're still able to do it, but now in chapter 3, I'll explain what those units mean and everything. So you could still do it. Any sort of conversion, doesn't matter what unit you have. I can make up units. I can say it's, lily bombs, right? Does not matter. What in the world is a lily bomb? I don't know. But if I tell you 1 lily bomb equals 5 miles, and I say I run 2 lily bombs, right? You can tell me how many miles I ran. So it doesn't matter what the units are. Don't get thrown off by units that you may have never seen. As long as I give you the conversions, you should be able to go from one unit to another, no problem. Okay, we're going to take a little break for math, but the dimensional analysis part, you're going to see on your quiz on Wednesday. Again, we're going from one unit to another. Don't make things complicated. I'll give you all the conversions. You're just going from one to another. Always just look at what's provided. Don't try to memorize conversions, because I can make up conversions. Like I did the lily bomb, right? I run 2 lily bombs. 1 lily bomb is 5 miles. How many miles did I run total? 10. Yeah, that's it. That's dimensional analysis. Significant figures, I'll give you a list of numbers. You just tell me how many significant figures in each number. And then I'll have a problem where you're doing mixed operations. You just tell me the correct answer to the correct number of significant figures. And then the density, again, looking at the equation, you should, if I give you 2 out of the 3 variables, you should be able to solve for the third one. So there's 3 parts to it, or 3 concepts that we're going to focus on. Okay, chapter 3. We initially take a little break from dimensional analysis or math, but we're going to get back into it. So if you notice, your lecture problems, chapter 3 has math on it. Math is very big in chemistry. Okay, we're going to look at states of matter. Now, anytime I say matter, that is anything that has mass to it and occupies space. The 3 states of matter we're going to focus on are solid, liquid, and gas. So look at the solid. They're freaked out. They're just really close to each other. Well, we don't like that, but it kind of contradicts it because solids do exist. If you look at a liquid here, notice the spacing between the actual atoms. The spacing increases. And then gases, the spacing increases even further. And notice these are actually moving. Let me scroll it up. I hate this divider. It's darker on top versus the bottom. So notice they're moving. They have velocity to it, a speed. Here you have the 3 states of matter in relation to water. So when you say the solid, that's ice, water, and steam. Here, the actual molecules are in a fixed state. Water is H2O, so the red dot is the oxygen, the blue are the hydrogens. So the molecules are in a fixed state. If you look at a liquid here, they're not in a particular shape, but they're close to each other, but the distance between them has actually increased. In the sense here, it looks like they're actually connected, but they're not. We'll talk about that later on in the semester, where we get into intermolecular forces, and those are attractive forces between the molecules. It actually looks like they're bonding between the molecules. And then you have a gas, which is steam. Here, notice the actual distance between the molecules is significant compared to the other two. And here they have actual speed, so notice they're trying to show that with this kind of fading color. Now, when we're looking at these 3 states, you want to know the basic characteristics of each one. Solid, it's going to be rigid. This has a fixed shape and volume. Meaning, if I have a solid, right, doesn't matter if I put it here or here, its shape is still the same. It's not going to morph into something else, right? I can put this in my bag, it's going to stay the same shape. I can put it in someone else's bag, the shape remains how it is. It has a fixed volume too. It has a certain volume to it. Doesn't matter where I move it, what bag I put it in, or let's say a big container, it's going to have a certain volume to it. So if I try to put this in here, is it going to fit? No.